In shallow water off the coast of Indonesia, something is crawling across the sand that should not exist. It has 6 arms tucked out of sight. 2 arms stretch out in opposite directions, banded black and white, moving like a snake ready to bite. A diver watches, frozen. This is not a snake. It is an octopus, wearing one. You're about to meet the only animal on Earth known to become more than one other creature. A flatfish gliding low, a lionfish bristling with poison spikes, a jellyfish drifting and stinging. All of it is one soft body, changing shape in seconds. Scientists did not even find this animal until 1998. Before that, it hid in plain sight for millions of years. We will follow it into a sea snake disguise built to freeze a predator's heart. We will trace the skin that may see light without using its eyes. We will meet 9 brains packed into one body, with 60% of its neurons living in its arms instead of its head. If you like the ocean's best-kept secrets, hit subscribe and stay close. 6 arms are about to disappear. 2 are about to become something else entirely. We begin. The water is warm and cloudy with silt. A diver hovers a few feet above a muddy slope, camera steady, breathing slow. Below, something flat and pale glides across the sand. It looks like a sole, one of those thin fish that press themselves flush against the seafloor. The diver keeps filming, more out of habit than excitement. Then the shape does something a fish cannot do. It grows arms. Within seconds, the flat gliding body pulls itself into a completely different form. Long limbs unfurl. Stripes of brown and white ripple across its skin. The thing that was a fish a moment ago is now, unmistakably, an octopus. This moment actually happened, off the coast of Sulawesi, Indonesia, in 1998. Divers exploring a muddy river mouth caught something on camera that had never been recorded before. They had found an octopus that could switch its body into the shape of another animal, then switch again into something else entirely. At first, nobody knew what to call it. It had no name in any science book. Word spread fast among divers, then researchers. Video clips passed from hand to hand. People argued about what they were even looking at. Was this one strange fish with a talent for disguise? Was it some kind of octopus nobody had documented? The confusion itself was a clue. This animal was not behaving like anything on record. Picture a school hallway where one student can instantly become someone else. Different face, different walk, different voice. Nobody would believe it until they saw it with their own eyes. That is what divers felt, watching this creature slide from fish to octopus to something else, all in the same 5 minutes. The muddy seafloor where they found it was not a beautiful coral reef. It was closer to a drainage ditch than a postcard. Grey, silty, plain. Most divers would swim right past a spot like that, looking for brighter water. That plainness turned out to be part of the secret. Nobody expected anything remarkable to be hiding in the mud. Scientists returned to that same stretch of seafloor again and again over the next 2 years. They filmed 9 different individuals, each one showing the same bizarre skill. This was not a one-time fluke, a single confused animal doing something strange by accident. It was a pattern, a survival strategy, a species doing something no other known animal on Earth had ever been caught doing on camera. The animal earned a name later, once researchers had studied it enough to describe it properly. But in that first year, it was simply the mystery from Sulawesi, a creature filmed pretending to be a fish, then unpretending, right in front of stunned eyes. Here is the detail that makes this stranger than it sounds. Camouflage, blending into rocks or sand, is common in the ocean. Hundreds of species do it. What this animal did was different. It was not hiding. It was actively performing, choosing a shape, holding a pose, moving like the animal it was copying, not just looking like it while sitting still. A 4-inch fish freezing to match a rock is camouflage. An 8-armed animal deliberately holding 2 arms straight out to imitate a snake's body, while tucking the rest of itself out of sight, is something closer to acting. That distinction sat at the center of everything scientists would spend the next several years trying to understand. Why would an animal need more than one disguise? What decided which shape to become? And how, exactly, was a boneless creature with no bones and no rigid skeleton at all pulling this off? The footage from that muddy slope in Sulawesi was just the opening scene. The real questions were only starting to surface. Somewhere off the coast of Indonesia, in shallow water anyone could wade into, an animal had been performing this trick for longer than anyone could measure. Not for decades, likely for millions of years, and no scientist had written it down. That fact alone stops people in their tracks. This is not a creature buried under the ice sheets of Antarctica. It is not thousands of feet down in crushing black water, where submarines rarely reach. It lives close to shore, in water shallow enough to stand in. So why did it take until 1998 for anyone to notice? Part of the answer is location. The creature favours muddy river mouths and silty bays, not the bright coral reefs that draw most divers and researchers. Coral reefs are colourful, photogenic, full of easy discoveries. Muddy slopes look empty, grey, uninviting. For decades, that meant almost nobody went looking there carefully. Think of it like a school library. Everyone crowds around the new releases at the front counter. Almost nobody wanders back to the dusty return bin nobody ever sorts. That is where this animal was hiding, in the dusty return bin of the ocean. The second reason is even stranger. The animal's whole survival strategy is built around not being noticed. Every disguise it uses exists to make a predator look away, hesitate, or swim past without a second glance. That same skill worked on humans for millions of years. It was not hiding from scientists on purpose. It was hiding from everything, and scientists just happened to be included. There is also a numbers problem. Even in the best-known dive spots, sightings remain rare. Divers who visit the same reef every week for years might see this animal only a handful of times. It does not gather in groups. It does not have bright, easy-to-spot colouring most of the time. Its natural resting colour is a plain, forgettable brown, the exact opposite of a warning sign. Compare that to a lionfish, with its bold red and white stripes and long spiky fins. A lionfish practically shouts at anyone nearby. This animal, most of the time, whispers. Diving technology itself is part of the story too. Before the 1990s, the kind of close, patient, slow-motion muck diving that reveals small creatures in silty water was far less common. Divers wanted big animals, sharks, rays, colourful reefs. The gear, the training, and the interest in slow-bottom crawling through mud all came together only in the last few decades of the 20th century. Once that shift happened, dedicated muck divers started spending hours hovering just above the seafloor, patient enough to watch a single patch of mud for long stretches. That patience is what finally caught this animal in the act. Here is the number that puts it all in perspective. The ocean covers about 70% of Earth's surface. Scientists estimate a huge share of ocean species remain undiscovered and unnamed, even today. An animal capable of impersonating over a dozen other creatures, living in shallow water close to shore, still slipped through that gap for as long as recorded science existed. That should change how anyone pictures the ocean floor, not as a fully mapped, fully catalogued place, but as a stage where extraordinary performers can go completely unnoticed, simply because nobody thought to watch the mud. Strip away every disguise and what remains is small, modest, almost unremarkable to look at. At rest, this animal stretches to about 2 feet long, arm tip to arm tip, roughly the length of a baseball bat. Most of that length is arms, thin and tapering, not body mass. Its main body, the part that holds its organs, is barely the size of a fist. Everything else is reach. Its natural colouring, before any performance begins, is a plain greyish-brown, sometimes marked with bands of white running down its arms. Nothing about that base look screams danger. It would not win a costume contest sitting still. It looks like driftwood, like a smear of mud that happened to grow arms. That plainness matters. This is a soft-bodied animal with no shell, no spines, no claws, and no bones anywhere in its body, not one. A crab has an armoured shell. A lobster carries claws that can crush. This animal has none of that. Its entire skeleton is water pressure, held inside flexible muscle, which is why it can squeeze through gaps barely wider than its own eye. Picture a stress ball made of thick rubber, filled with only enough structure to hold its shape. That is roughly what this animal's body works like. no rigid frame at all. Without a shell, without venom of its own, without claws or teeth built for real combat, this animal is, in the most basic sense, defenseless. Any predator that catches it in open water can likely end the fight in seconds. A boneless body might sound flexible and clever, but out in open water it also means soft, easy to bite through, easy to swallow whole. That vulnerability is the entire reason the disguises exist. Every impersonation this animal performs, every shape it borrows from more dangerous creatures, exists because its actual body offers almost no defense on its own. Compare it to a kid at school without a Letterman jacket, without a car, without an older sibling backing them up in the hallway. If that kid wants to avoid trouble, the smartest move is not brute strength. It is knowing exactly who to imitate and when, so bigger threats decide to leave them alone. The eyes tell part of the story too. Like all octopuses, this animal has large, complex eyes capable of detecting shapes, movement, and contrast with impressive precision. Those eyes feed constant information about the surrounding reef, the mud, the shifting light, and anything approaching from any direction. Underneath the skin sits something even stranger. Layers of specialized cells that let this animal shift color and texture almost instantly. That system will matter enormously later. For now, picture it as a built-in costume department, tucked just beneath the surface of the skin, ready to be called into action the instant danger appears. So the true shape, the one underneath every borrowed disguise, is a small, soft, boneless animal with excellent eyesight and no real weapons, fragile in almost every traditional sense, and yet somehow this fragile creature survives in one of the most predator-filled environments on the planet. Long before any research paper existed, local fishermen in parts of Indonesia already knew something was strange about the mud near shore. They just did not have the scientific language for it yet. Fishermen spend entire lifetimes reading the same stretch of water. They know where fish hide, where crabs burrow, where a snake might surface for air. That kind of knowledge, passed down for generations, notices patterns that outsiders miss completely. Some fishermen in the region had reportedly seen this animal's tricks long before any diver caught it on film. But a shape-shifting octopus was such an unlikely story that it rarely travelled far beyond the docks where it happened. Imagine trying to convince your entire school that a kid in the hallway can turn into 3 different people depending on who is watching. Without video proof, most people would assume you were exaggerating or simply mistaken. That is roughly the position local observers were in for years. The core of the trick lies in something zoologists call dynamic mimicry, the ability to switch between multiple different disguises depending on the exact threat nearby. This animal does not just have one impressive costume, it has an entire wardrobe, and it knows which outfit to grab based on who just walked into the room. Researchers eventually documented this by watching how the animal responded to specific attackers. When a territorial damselfish came at it aggressively, the octopus would transform into the banded shape of a sea snake, a known predator of that exact fish. When a more generic threat approached, it would switch instead to a flattened gliding shape, or spread its arms to mimic the poisonous spines of a lionfish. That detail changes everything about how impressive this behavior really is. This is not a fixed reflex, like a chameleon defaulting to green because it usually sits in leaves. This is closer to reading the room, recognizing exactly what is approaching, then selecting the specific costume that particular threat is most likely to fear or avoid. Only one other animal on record, a close relative called the Octopus, has ever been documented doing anything similar. Everything else in the ocean that uses camouflage sticks to one look, one strategy, repeated the same way every time. Here is a comparison that makes the scale of this clear. A pufferfish has one defense, inflate and display spines. A skunk has one defense, spray. This animal effectively carries more than a dozen different defenses in a single body, and picks the correct one in real time in the middle of an active threat without any time to plan ahead. The fishermen who first noticed something strange near shore were not imagining things. They were witnessing, without knowing it, one of the most sophisticated defensive behaviours ever recorded in the animal kingdom, playing out in ordinary water a few feet from where boats were tied up every single day. Science eventually caught up to the stories. The mud kept it secret only until someone finally pointed a camera at exactly the right moment. Danger arrives fast in shallow water. A damsel fish, small but fiercely territorial, darts toward the octopus in open aggression. There is no time to think. There is only time to react. Within seconds, 6 of the octopus's 8 arms disappear. Not literally, but functionally, tucked tightly into a burrow or pulled flush against the body, hidden from view entirely. The remaining 2 arms stretch outward in opposite directions, one pointing left, one pointing right, forming a long, straight line across the seafloor. Colour floods across those 2 arms almost instantly, alternating bands of black and white rippling down their length. The octopus begins to undulate those arms with a slow, side-to-side rhythm, the exact motion of a swimming sea snake. To any fish nearby, especially one that has learned to fear sea snakes through hard experience, the message lands immediately. A venomous banded sea snake, coiled and moving, sits right where the octopus used to be. Sea snakes carry a reputation earned through real danger. Their venom can be lethal to fish many times their size, and most reef creatures give them a wide, cautious berth on instinct alone. By borrowing that exact reputation, the octopus effectively rents fear it never had to earn itself. Picture a smaller kid at school wearing a jacket from the toughest senior on campus. Nobody checks whether the kid inside the jacket is actually tough. The jacket alone changes how people react before a single word gets spoken. What makes this transformation remarkable is the precision involved. The octopus does not simply turn black and white and hope for the best. It selects this exact disguise specifically when facing predators known to fear sea snakes, according to researchers who tracked which threat triggered which costume. That kind of targeted response suggests something closer to decision-making than blind instinct. The physical mechanics behind the trick matter too. An octopus arm is an extraordinary tool, made almost entirely of muscle, with no bones to restrict its movement. That flexibility lets it curl, flatten, ripple, or hold rigid, whatever the disguise requires. 2 arms stretched into a straight, undulating line create a shape a fish brain instantly recognizes and reacts to, even though the actual owner of those arms is hiding just out of sight. The whole performance rarely lasts long. A predator convinced by the display usually turns away within seconds, deciding this is not a fight worth having. Once the threat clears, the octopus can unfurl its hidden arms and continue exactly what it was doing before the interruption, hunting, exploring, moving toward its burrow. There is something almost theatrical about the whole sequence, a costume built entirely from body parts, a performance aimed at a single specific audience, a curtain that drops the instant the danger passes, and this sea snake routine is only the beginning. Different threats call for entirely different disguises, and the next one trades subtlety for something far more visibly dangerous. Fear, in the ocean, is not random. It gets built over generations, shaped by real encounters between predators and prey. Understanding why the sea snake disguise works so well means understanding exactly how that fear gets written into a fish's brain in the first place. Banded sea snakes are genuinely dangerous. Their venom ranks among the most potent found in any marine animal, capable of shutting down a smaller creature's nervous system within minutes. Fish that survive a close encounter, or watch a nearby fish fail to survive one, carry that lesson forward. Avoid the black and white bands. Avoid the slow, deliberate weaving motion. That pattern means danger. This is where the octopus's trick becomes almost unfair in the best possible way. It does not need to convince a predator through careful persuasion. It only needs to trigger a reaction that evolution already wired into that predator's brain automatically, without conscious thought. Compare it to a fire alarm going off in a school hallway. Nobody stops to verify there is an actual fire. Feet move toward the exit immediately because the sound itself has been trained into everyone as a signal demanding instant response. The octopus, essentially, sets off a similar alarm using shape and colour instead of sound. Researchers observed something particularly telling. This exact disguise appears most often when the octopus is threatened by species that specifically fear sea snakes, damselfish among them. That is not a coincidence. It strongly suggests the octopus is not randomly flipping through a costume box. It is choosing the one specific outfit most likely to trigger fear in whatever creature happens to be attacking at that moment. That kind of targeted matching raises a genuinely difficult question researchers still debate. Does the octopus somehow recognize which predator is nearby and consciously select the most effective response? Or has evolution simply wired certain triggers, like aggressive movement from a damselfish, directly to certain disguises without anything resembling real-time thought involved? Nobody has a fully confirmed answer yet. What is confirmed is the result. Across repeated observations, the sea snake impression reliably drives away exactly the kind of predator most likely to fear the real animal. There is a broader lesson buried in this single behaviour. Survival in the ocean rarely depends on being the strongest or fastest creature present. It depends on understanding exactly what your specific audience already fears, then giving them precisely that, at precisely the right moment. An animal with no venom, no bite worth mentioning, and no armour at all has turned borrowed fear into one of the most effective defences on the entire reef. It never needed real danger of its own. It only needed to understand danger well enough to fake it convincingly. And a sea snake is far from the only costume in the collection. Waiting just behind it is a disguise built around spines, poison, and a very different kind of warning altogether. A different threat approaches. This time no snake-fearing fish darting in with aggression, but a more generalized predator cruising open water, scanning for an easy meal. The sea snake trick, built for a specific fear, will not work here. So the octopus reaches for a different disguise entirely. Instead of hiding 6 arms and stretching 2 into a line, the octopus spreads all 8 arms outward at once, wide and fanned, radiating from its body like spokes on a wheel. Each arm stiffens slightly, held at odd angles that echo something sharp and dangerous. The shape it is copying belongs to the lionfish, one of the most visually striking and genuinely hazardous fish on any tropical reef. A real lionfish carries long, needle-thin spines running along its back and sides, each one capable of delivering venom powerful enough to cause serious pain, swelling, and illness in anything foolish enough to bite down. Lionfish rarely hide from anything. Their entire survival strategy runs in the opposite direction from camouflage. Bold red and white stripes, spines held outward, a slow and unbothered drift through open water. Nothing about a lionfish tries to blend in. Everything about it announces a clear warning. Touching me will hurt. The octopus borrows that exact confidence. By fanning its arms into a similar radiating pattern, it recreates the rough silhouette of all those dangerous spines, without possessing a single one of them. This disguise does not need to fool a predator completely. It only needs to introduce enough doubt to make attacking feel like a bad gamble. Think about a bike locked up with a chain that looks heavy-duty, thick links, a serious-looking padlock, even if the metal underneath happens to be softer than it appears. Most people walking past will not bother testing it. The look alone does the actual work of preventing the attempt. Underwater, that kind of hesitation can mean the difference between survival and becoming a meal. A predator that pauses even briefly, uncertain whether those spread arms hide real venom, gives the octopus a crucial window. Enough time to retreat toward a burrow, slip behind a rock, or simply drift out of the danger zone entirely. What makes this disguise especially interesting is its flexibility. Unlike the sea snake impression, which seems tied to one very specific type of predator, the lionfish costume appears to work as a more general warning, useful against a wider range of threats that share a basic caution around spiky, brightly patterned animals. The octopus, in other words, keeps more than one tool in its kit, a precision tool built for a single specific fear, and a broader tool built to work reasonably well against almost anything uncertain about approaching something covered in apparent spines. One disguise borrows fear from a snake's venom. This one borrows fear from a fish that never hides at all. 2 completely different strategies, both built from the same soft, boneless body, deployed depending entirely on what danger happens to be swimming closest. Here is the detail that turns this entire performance into something genuinely remarkable. Every disguise built around danger, the sea snake, the lionfish, and others still to come, works despite one simple fact. This octopus carries no venom capable of matching either animal it imitates. Its actual defences amount to very little. A weak bite, unlikely to cause serious harm to most predators. A cloud of ink it can release to create momentary confusion during an escape. Beyond that, nothing resembling a real weapon exists in its body. And yet, across countless recorded encounters, disguises built entirely around borrowed danger consistently succeed at driving predators away. That result forces an uncomfortable but fascinating conclusion. In the ocean, the appearance of danger can function almost as effectively as danger itself. This works because most predators cannot afford to test every warning sign they encounter. A single mistake, biting down on an animal that actually is venomous, can cause serious injury or death. Evolution has shaped predator brains to treat certain colours, shapes, and movements as reliable danger signals, then avoid them automatically, without pausing to verify accuracy every single time. Think about a stop sign standing at an empty intersection late at night. No police car waits nearby to enforce it. No immediate consequence follows running through it unnoticed. Most drivers still stop anyway, because the shape and colour alone carry enough built-in authority to trigger the response, regardless of whether real enforcement happens to be watching. Fish operate on a similar principle, shaped by millions of years instead of traffic laws. Black and white bands moving in a snake-like rhythm. Red and white spines fanned outward. These patterns carry enough evolutionary weight that most predators simply will not risk finding out whether the specific animal in front of them today happens to be the real dangerous version or a convincing imposter. This is precisely why an animal with no venom worth mentioning can survive in water absolutely full of creatures that could otherwise overpower it in seconds. The octopus is not lying exactly, at least not in words. It is presenting a set of visual signals its own body evolved to reproduce, signals that other species already learned to fear through entirely separate, unrelated evolutionary paths. There is something worth sitting with here. Deception, in this case, is not cruelty or trickery in any human sense. It is closer to elegant efficiency. Rather than evolving actual venom, which takes enormous biological investment across countless generations, this animal evolved the ability to borrow venom's reputation instead, on demand, exactly when needed. A costume that only needs to work for a few critical seconds, aimed at a brain already primed to believe it, accomplishes something a real weapon would take far longer to develop. And the costume closet does not end there. The next disguise trades danger and spines entirely for something built purely around speed and disappearing into open sand. Not every threat calls for a warning. Sometimes the smartest move is to stop looking dangerous altogether, and instead look like something not worth chasing at all. To pull off this disguise, the octopus pulls all 8 arms in tight behind its body, pressing them together into a single, narrow, tapering shape. Its body flattens against the seafloor, edges smoothing out, colour shifting into a pale, sandy tone that matches the ocean bottom beneath it. Then it moves, using jet propulsion, pushing water out through a small funnel on its body to glide forward in a smooth, gliding rush across the sand. The shape it becomes belongs to a sole, a flat-bottom-dwelling fish built for exactly this kind of low, fast travel across open ground. Soles are common, unremarkable, and rarely worth a predator's effort to chase down. A sole slipping across the sand draws far less attention than a soft, exposed octopus caught out in the open. This disguise flips the entire strategy used in earlier chapters. The sea snake and lionfish impressions work by announcing danger loudly, daring a predator to risk an attack. This one works by doing the opposite, disappearing into ordinary background noise, becoming a shape too plain and too fast to bother pursuing. Picture a hallway crowded with students between classes. Someone trying to avoid a confrontation does not always need to look intimidating. Sometimes the better move is blending into the crowd entirely, moving with everyone else, becoming impossible to single out. Speed plays a critical role here that the other disguises do not require. A sea snake impression can hold still, arms extended for several seconds at a time. This disguise depends on motion. The octopus needs to cover real distance quickly, crossing open, exposed sand where any predator has a clear line of sight, before something faster catches up. Jet propulsion makes that possible. By forcing water through its funnel in short, powerful bursts, the octopus can accelerate rapidly across short distances, far faster than its normal crawling pace across the seafloor. Combined with a flattened, sole-shaped silhouette, the entire performance reads as one continuous forgettable blur crossing open ground. There is a hidden efficiency in choosing this disguise specifically for open, exposed terrain. Bright warning colours work best when a predator has time to notice and process them. Out in open sand, with nowhere to hide, and a predator potentially closing in fast, speed and plainness can matter more than any dramatic warning display. Different terrain, different threat level, different costume entirely. The octopus reads not just what predator is nearby, but what kind of environment it currently occupies, then adjusts accordingly. This flattened, fast-moving impression captures something important about the overall strategy at work here. Survival does not always mean looking scarier. Sometimes it means looking boring enough that nothing bothers to look twice. Every disguise covered so far shares one thing in common. They all rely on convincing a predator to hesitate, to reconsider, to decide an attack carries too much risk. The sole fish impression breaks that pattern entirely, and understanding why reveals something deeper about how this animal thinks through danger in the real time. A sea snake or lionfish, disguise works through psychology. It plants doubt in a predator's mind, buying time through fear rather than physical distance. But that strategy has a weakness. It only works if the predator actually pauses to consider the warning. Some threats move too fast or attack too aggressively for hesitation-based tricks to matter much at all. Against those faster, more committed predators, the octopus switches its entire approach from persuasion to pure evasion. Rather than trying to change what a predator believes, it simply tries to outrun the situation using speed and blending together at once. This is the difference between talking your way out of a confrontation and simply running. Both are valid strategies. Which one works depends entirely on the specific threat standing in front of you and how much time that threat is likely to give you before committing to an attack. Researchers who studied this behaviour noted something significant. The octopus does not default to one single strategy across every encounter. It appears to assess the situation, the type of predator, the surrounding terrain, the available time, then select whichever approach offers the best odds of survival in that specific moment. That kind of flexible, situation-dependent decision-making is unusual, even among animals generally considered intelligent. Many creatures rely on a single, fixed defense, deployed the same way every time regardless of context. A pufferfish always inflates, a skunk always sprays. This octopus, by contrast, appears to weigh its options and choose accordingly, closer to strategy than reflex. Consider how differently a person might react to a threat depending on the setting. Someone confronted in a crowded, familiar space might stand their ground, using confidence and presence to diffuse the situation. That same person, caught alone in an unfamiliar alley, would likely choose to run instead. Same person, same underlying instinct towards self-preservation, two entirely different responses shaped by circumstance. The octopus demonstrates something similar, playing out across an 8-armed, boneless body instead of 2 legs. Bluff when bluffing offers the better odds. Run when running does. This flexibility likely explains part of why this particular species survives so well despite carrying no real weapons of its own. A fixed strategy works only against threats it happens to match well. A flexible strategy, capable of shifting between deception and raw speed depending on the moment, works across a far wider range of dangers. Speed, then, is not simply an escape mechanism bolted onto this animal's disguise collection. It represents an entirely different branch of the same underlying skill, choosing precisely the right tool for exactly the right threat moment by moment, with no time to spare for a wrong guess. Some threats come from above, drifting down through open water rather than crawling along the seafloor. Against those, the octopus reaches for a disguise unlike anything covered so far, one built not around speed or bold colour, but around shape and motion alone. To become this impression, the octopus lifts itself off the bottom and allows its arms to trail loosely beneath its body, drifting with the current rather than moving with purpose. Its outline softens, rounding out, echoing the bell-shaped body and dangling tentacles of a jellyfish pulsing slowly through open water. Jellyfish carry their own well-earned reputation. Many species deliver painful, sometimes dangerous stings through their trailing tentacles, and most reef creatures give them a healthy amount of space rather than risk contact. That instinctive caution, built through countless painful encounters across generations, is exactly what the octopus taps into here. What makes this disguise particularly clever is how little effort it requires. Unlike the rigid extended arms of the sea snake impression, or the fast, deliberate jetting of the soulfish disguise, the jellyfish impression relies mostly on stillness and drift. The octopus does not need to fight against the current or hold a difficult pose. It simply lets its arms hang loose and allows the water itself to do most of the work. Picture someone at a pool party floating quietly on their back, arms trailing beneath the surface, doing nothing more athletic than simply existing in the water. From a distance, that stillness alone can be enough to change how others perceive the situation, without requiring any dramatic effort at all. Scientists have observed mimic octopuses displaying jellyfish-like posture, though this particular disguise remains less thoroughly documented than the sea snake or lionfish impressions. Divers and researchers have reported the behaviour, but confirming exactly how often it appears, and against which specific threats, remains an area still being studied. That gap in certainty is worth sitting with honestly. Not every disguise in this animal's repertoire has been observed and confirmed with equal depth. Some behaviours, like the sea snake response to territorial damselfish, come from carefully documented repeated observation. Others, including parts of the jellyfish impression, rest on a smaller number of sightings, still valuable, but not yet studied as thoroughly. That uncertainty does not diminish how remarkable the behaviour appears. If anything, it points towards something even bigger. Researchers suspect this animal's full range of disguises may extend beyond what has been documented so far, simply because catching rare behaviours on camera, in murky water, during unpredictable moments of threat, remains genuinely difficult work. The jellyfish impression, drifting and passive, sits in sharp contrast to almost every other disguise in this collection. It asks for no bold performance, no aggressive posture, no burst of speed. It simply asks the octopus to stop fighting the water and let an old, painful memory living inside a predator's brain do the rest of the work automatically. Few animals in the entire ocean carry a reputation for raw physical violence quite like the mantis shrimp. This next disguise borrows directly from that fearsome legacy. A real mantis shrimp possesses a set of specialised front limbs capable of striking with tremendous speed and force. Some species can throw a punch so fast it briefly heats the surrounding water and creates a small shockwave, strong enough to crack aquarium glass in captivity. Reef creatures that have witnessed a mantis shrimp in action, or survived a close encounter, tend to remember the lesson permanently. To mimic that fearsome reputation, the octopus adjusts its posture and arm positioning to echo the mantis shrimp's compact coiled stance, arms drawn in tighter, body angled low and ready, projecting the same coiled, dangerous energy the real animal carries naturally. Colour shifts reinforce the illusion further, patterns and tones adjusting to resemble the mantis shrimp's own distinctive colouring. This disguise operates on a slightly different principle than the sea snake or lionfish impressions. Those relied heavily on visual pattern, bold stripes or spread spines, communicating danger from a distance. The mantis shrimp impression leans more on posture and readiness, a coiled, alert stance that suggests explosive violence waiting just beneath the surface, ready to strike at the first wrong move. Think about how a person standing with clenched fists and a tense, ready posture communicates something entirely different from someone standing relaxed with open hands, even before either person says a single word. Body language alone can shift how a threat gets perceived, sometimes more effectively than words ever could. The octopus applies that same principle underwater. A predator approaching does not need to see an actual mantis shrimp punch delivered to feel the warning land. The coiled, ready posture alone carries enough evolutionary weight, built through countless encounters other creatures have had with the real animal, to make most predators think twice before committing to an attack. What makes this particular disguise especially interesting is what it reveals about the sheer range of reference material this octopus appears to draw from. Sea snakes, lionfish, jellyfish, mantis shrimp. 4 entirely different animals, 4 entirely different survival strategies, poison, spines, stinging tentacles, and crushing physical force, all somehow encoded into the behavioural toolkit of one soft-bodied, boneless creature. No other animal studied so far demonstrates anything close to this breadth. Most mimics throughout the animal kingdom copy exactly one other species refined and specialised over countless generations for that single specific disguise. A stick insect looks like a stick, permanently, its entire body built around that one trick. This octopus instead appears to carry an entire mental library of postures, colours, and movement patterns, each one associated with a different marine species, ready to deploy whichever entry fits the specific threat currently approaching. That range raises a genuinely difficult question that connects everything covered across every disguise so far. How does a brain, especially one built so differently from a human brain, store and recall that many distinct behavioural templates, then select the correct one instantly, under real pressure, with no time to consult anything resembling a manual? That question leads directly into some of the strangest biology on this entire creature. Biology that later chapters will explore in far greater depth. Every disguise covered so far has served one clear purpose: defense against something bigger and more dangerous. This next trick flips that entire logic on its head. Sometimes the octopus is not the one trying to avoid becoming a meal, it is the one hunting for its next one. According to observations documented by researchers, the octopus can adjust its shape and movement to resemble a crab, specifically positioning itself in a way that mimics a potential mate rather than a predator. A real crab searching for a partner reads certain visual and behavioural signals as safe, even inviting cues built through its own evolutionary history of finding and approaching mates successfully. The octopus, understanding none of this consciously in any language sense, but shaped by evolution to exploit it anyway, recreates just enough of those signals to draw a curious crab closer. The crab, expecting a promising encounter, closes the distance itself, walking directly into range instead of needing to be chased down or ambushed through brute force. What happens next is abrupt and final. The disguise drops instantly, and the octopus attacks, using the exact closeness the crab itself chose to approach with. There is something almost startling about the psychology at work here. An animal using apparent romantic interest to bypass what should otherwise be one of the ocean's most cautious defensive creatures. Crabs are not easy prey under normal circumstances. Their shells offer real physical protection, and most crab species remain alert to nearby threats, ready to scuttle away or raise defensive claws the instant danger appears. Approaching a crab directly, as an obvious predator, often ends with the meal escaping into a crevice long before the octopus gets close enough to strike. This decoy trick sidesteps that entire problem. Rather than closing the distance itself and risking detection, the octopus lets the prey do the dangerous work of closing that gap voluntarily, believing the entire time that it is walking toward opportunity rather than toward danger. Picture a fishing lure shaped and coloured to look exactly like the small prey a base wants to eat. The fish approaches on its own, convinced by the shape and motion, and gets caught the moment it commits. This crab decoy trick works on a strikingly similar principle, just built entirely from a living shape-shifting body instead of painted plastic and a hook. This particular use of mimicry stands apart from every other disguise covered so far in one crucial way. It does not exploit fear. It exploits attraction, curiosity, and the simple biological drive to find a mate. That distinction matters. It shows this animal is not limited to a single emotional lever. It can trigger caution when caution serves its survival, and it can just as easily trigger curiosity when curiosity serves its hunger instead. An animal capable of manipulating both fear and attraction, depending entirely on whether it is trying to avoid becoming dinner or trying to catch its own, demonstrates a level of behavioural range that continues to challenge how scientists think about intelligence outside the human brain and outside vertebrate animals altogether. Add up every documented impression: sea snakes, lionfish, flatfish, jellyfish, mantis shrimp, crabs, and researchers arrive at a running total. Studies have confirmed this octopus successfully impersonating at least 16 distinctly different animals, including stingrays, brittle stars, hermit crabs, sea anemones, blennies, and snake eels, among others. 16. Stop and let that number sit for a moment. Most animals throughout the entire animal kingdom that use mimicry as a survival strategy copy exactly one other species, and only one, refined across countless generations into a single, specialized trick. A walking stick insect resembles a twig, permanently, for its entire life, across its entire species. That is the norm. One animal, one disguise, forever. This octopus obliterates that pattern entirely. 16 separate, distinct impressions confirmed through direct observation, each one calling for a different arrangement of arms, a different colour pattern, a different style of movement entirely. No other confirmed case throughout the documented animal kingdom comes close to matching that range, except possibly its close relative, the Octopus, a similar species suspected of comparable abilities, but studied in far less depth so far. Here is where the story turns even stranger. 16 represents only the confirmed count, the number researchers have personally witnessed, filmed, and verified closely enough to document with confidence. Divers and scientists studying this animal in the wild suspect the true number likely runs higher still. Multiple factors feed that suspicion. This animal remains genuinely rare to encounter, even in locations considered reliable hotspots for sightings. Much of its natural habitat, muddy river mouths and silty coastal bottoms, offers poor visibility, especially compared to the crystal clear water surrounding a typical coral reef. Many potential disguises may simply be happening regularly, in murky conditions, without a camera anywhere nearby to catch them clearly enough for confirmation. Consider how differently a talent might get counted depending entirely on who happens to be watching and when. A student who can play 5 different instruments might only get credited with 2, simply because nobody happened to catch them practicing the other 3. The actual skill exists regardless of who witnesses it. Documentation always lags behind reality, sometimes by a significant margin. That gap between confirmed behaviour and likely reality applies directly here. 16 disguises stands as an impressive scientifically verified number. It almost certainly is not the complete, final total. This uncertainty points towards something bigger than just one octopus species and its collection of tricks. It suggests that even well-studied animals, ones actively followed by dedicated researchers for years at a time, can still hold back secrets, revealing new behaviours only slowly, disguise by disguise, sighting by sighting, patience rewarded only occasionally. 16 confirmed, possibly more waiting. The next question becomes just as difficult to answer. How exactly does this animal decide which one of those 16 or more disguises fits the specific moment it finds itself in? Every disguise covered across this journey demands something remarkable happening beneath the surface, a decision made correctly, made fast, with real consequences riding on getting it right. Consider the actual timeline involved. A predator does not send a polite warning before attacking. Threat and response happen within the same narrow window, often just a few seconds total. Within that brief span, the octopus must somehow identify what kind of danger has appeared, select the single most effective disguise from its entire repertoire, then execute that transformation completely, accurately, convincingly, before the predator commits to striking. Researchers observed a pattern strong enough to draw real conclusions from. Specific predators reliably triggered specific disguises, not randomly, not interchangeably. Territorial damselfish, prone to charging in aggressively, consistently drew out the sea snake impression. Since sea snakes rank among the natural predators, damselfish are wired to fear most. Different, more generalized threats drew different responses entirely. Lionfish spines, flattened soul shapes, or other impressions better suited to that particular situation. That consistency matters enormously. Random guessing would not reliably produce matched pairs between specific predator types and specific disguises, repeated across multiple individual octopuses, observed over multiple encounters, across different locations. A genuine pattern like this suggests something closer to assessment and selection than simple, blind reflex. Picture a goalkeeper facing a penalty kick. There is no time to consciously calculate angle, speed, and trajectory using careful math. Yet trained goalkeepers still dive the correct direction far more often than random chance alone would predict, drawing on pattern recognition built through repetition and situational awareness, all compressed into a fraction of a second. Something comparable may be happening inside this octopus, though built from a nervous system almost nothing like a human brain. Whether the process should be called true conscious decision-making, in any sense resembling human thought, remains a genuinely open, actively debated question among scientists who study this behaviour closely. What is not up for debate is the result. The right disguise, matched reliably to the right threat, deployed within a survival critical window measured in mere seconds. Whatever is actually happening inside that boneless distributed nervous system It is producing outcomes that look, from the outside, remarkably like careful strategy. This speed and precision becomes even more remarkable once the full picture comes into focus. This is an animal with no centralized brain in anything resembling the human sense, no spinal cord, no bones providing rigid structural reference points for its own body. And yet it consistently threads a genuinely difficult needle: correct threat assessment, correct disguise selection, correct physical execution, all compressed into a life or death handful of seconds. Later chapters dig directly into the biology making this even remotely possible. The strange, distributed nervous system spread throughout its arms, and the skin that may be doing far more independent work than anyone initially suspected. Every disguise depends on one crucial, often overlooked ingredient. Before the octopus can respond correctly to a threat, it first has to actually detect and identify that threat accurately, using senses built for an entirely different kind of world than the one humans experience. Octopus eyes rank among the most sophisticated found anywhere in the invertebrate world, capable of detecting shape, movement, and contrast with real precision. Even in the murky, silt-filled water, this species typically calls home. Those eyes stay in near constant motion, scanning the surrounding environment continuously for any sign of approaching danger. But eyesight alone does not fully explain how this animal identifies threats so specifically. Recognizing simply that something is approaching would only ever justify a single, generic, defensive response, hardly enough to explain 16 distinct, carefully matched disguises triggered by 16 very different situations. Instead, this animal appears to distinguish between different types of predators specifically, responding differently depending on exactly which threat has appeared. That level of discrimination suggests genuine pattern recognition, happening in real time, not simply detecting movement in general, but identifying the particular shape, size, and behavior pattern belonging to a specific type of approaching animal. Think about how quickly a person can recognize a familiar face from a distance, well before any individual facial feature becomes fully clear. The brain fills in identity based on overall shape, posture, and characteristic movement patterns, built through repeated past exposure to that same face. Something functionally similar may be happening when this octopus distinguishes a territorial damsel, fish's aggressive, direct charge from a slower, more generalized predator's cautious approach. This raises a genuinely fascinating question that connects directly back to intelligence itself. Recognizing a general threat requires only basic sensory processing, hardly a skill unique to sophisticated animals. Recognizing a specific type of threat, then correctly matching that specific threat to the single most effective response out of an entire mental library of options, requires something considerably more sophisticated happening underneath the surface. Scientists studying this exact question point toward the octopus's genuinely large, complex nervous system, relative to its overall body size, among the most complex nervous systems found in any invertebrate species studied so far. That complexity likely plays a direct role in this animal's demonstrated ability to assess situations quickly and respond appropriately, rather than relying purely on fixed, unchanging instinct. There is something worth sitting with here. This entire elaborate performance, sea snake, lionfish, mantis shrimp, crab decoy, and every other disguise covered throughout this journey depends entirely on one foundational skill operating correctly and quickly beneath the surface, correctly identifying exactly what is approaching before deciding exactly how to respond to it. Without that underlying recognition working reliably, every other impressive trick in this animal's collection would simply fail to trigger at the right moment, or worse, trigger against entirely the wrong threat. The disguises themselves may be the most visually dramatic part of this story, but perception and correct identification quietly does just as much of the real work, mostly unseen, happening in the crucial seconds before any transformation even begins. Every disguise covered across this entire journey depends on one remarkable physical system, hidden just beneath the surface of the octopus's skin. Without it, every single transformation described so far would be biologically impossible. Just underneath the outer layer of skin sit specialized cells called chromatophores, tiny sacs filled with pigment, typically red, yellow, orange, brown, or black. Each individual sac sits surrounded by a small ring of muscle. When that muscle contracts, the sac stretches wide, exposing its full color across the surrounding skin. When the muscle relaxes, the sac shrinks back down, hiding most of its color from view. This octopus, and its close relatives, may carry millions of these chromatophores spread across the entire body, each one controlled individually through its own dedicated nerve connection. Millions of tiny, independently controllable colored dots, arranged like an almost impossibly high-resolution screen, built entirely from living muscle and pigment instead of electronics. Picture the biggest stadium scoreboard ever built, made of individual light bulbs that can each switch on or off independently, fast enough to create moving images and full animations across the entire surface. Now shrink that same basic concept down to fit across a single, 2-foot-long boneless body and swap electric bulbs for living, muscle-controlled sacs of pigment instead. That comparison genuinely undersells the situation. Cephalopod skin, the specialized skin found in octopuses, squid and cuttlefish, holds a significantly higher density of these controllable pigment cells per square inch than almost any other tissue found anywhere else in the animal kingdom. This extraordinarily high density is precisely what allows for such sharp, detailed, high-resolution color patterns, the kind of precise definition genuinely needed to convincingly recreate the specific, banded stripes of a sea snake, or the fine-textured patterning of a lionfish's spines. Speed matters here just as much as resolution does. Because each individual chromatophore connects to its own dedicated nerve, color changes can ripple across the entire body in well under a second, fast enough that a predator watching closely might see the transformation begin, yet still fail to react quickly enough before it fully completes. This system explains, at least partially, how 6 arms can seemingly vanish, while 2 others transform into convincing sea snake bands within mere seconds. It is not 6 arms literally disappearing in any physical sense. It is skin color and posture shifting together so quickly and so precisely that the visual effect reads as an instant, complete transformation to any observer watching in real time, predator or diver alike. What remains genuinely astonishing is the coordination required to pull this off successfully. Millions of individual cells, each one controlled by its own separate nerve connection, somehow firing together in exact, precise patterns to create one single, coherent, convincing image across the entire body in a fraction of a second, under direct threat with essentially zero room for error. This raises an obvious, pressing question. What kind of nervous system could possibly coordinate that level of complexity, that quickly, especially inside an animal with no centralized brain in anything resembling the traditional vertebrate sense? The answer turns out to be even stranger than the chromatophores themselves, and it involves a nervous system unlike almost anything else found across the entire animal kingdom. Color alone does not fully explain the depth and richness of every disguise covered so far. Underneath the chromatophores, 2 additional layers of specialized cells work together, adding a level of visual complexity that pigment alone could never achieve on its own. Beneath the chromatophore layer sit iridophores, cells packed with tiny reflective plates made from a specialized protein. Rather than containing pigment themselves, iridophores work more like microscopic mirrors, bending and reflecting specific wavelengths of light depending on exactly how those internal plates happen to be spaced and angled. This is what produces shimmering blues, greens and metallic tones, colours that pigment alone genuinely cannot create. Below that sits a 3rd layer, leucophores, white reflecting cells that scatter light evenly across all wavelengths at once. These cells act as a bright, neutral background canvas, making every colour layered above appear sharper, more vivid, and more clearly defined against the surrounding water. Picture painting a mural directly onto plain grey concrete, versus painting that exact same mural onto a bright white primed wall first. The colours technically remain identical in both cases, yet the white background version reads far more vivid, more precise, more immediately eye-catching. Leucophores function as that essential white background layer, built directly into the octopus's own skin. Together, these three distinct layers, chromatophores controlling pigment, iridophores controlling reflected light, and leucophores controlling overall brightness and contrast, combine to produce nearly any colour, pattern or texture found across the surrounding reef environment. This layered system helps explain how disguises manage to look so convincingly detailed and lifelike, rather than simply a rough, blurry approximation of the intended target. The lionfish impression benefits enormously from this three-layer system. Real lionfish display sharp, high-contrast red and white banding, exactly the kind of vivid, precise definition that requires coordinating pigment, reflected light, and background brightness working together in harmony. A single pigment layer alone, without the iridophores and leucophores supporting it, would likely produce something closer to a dull, muddy approximation rather than a genuinely convincing costume. What makes this three-layer system especially remarkable is the coordination required behind it. Each layer operates through its own separate mechanism: muscle contraction for chromatophores, structural reflection for iridophores, light scattering for leucophores, yet all three must somehow activate together in the correct combination within a fraction of a second to produce one single, coherent, convincing image. Scientists studying cephalopod skin broadly, not limited to this one species alone, have noted that some species have even evolved the ability to tune their iridophores dynamically, adjusting reflected colour in real time rather than relying on a single fixed reflective pattern. Research into exactly how finely this particular octopus can control that specific ability remains ongoing. Three separate biological systems, layered directly on top of one another, working in tight coordination to produce a single convincing illusion. And colour represents only half of the full disguise. The other half depends on texture, an entirely separate biological trick still waiting to be explored. Colour alone cannot complete every disguise. Some impressions demand more than the correct pattern. They demand the correct feel, the correct silhouette, the correct texture, all shifting to match whatever this animal happens to be imitating in that specific moment. Octopus skin contains a separate set of structures entirely, tiny muscular bumps called papillae, scattered across the body's surface. When relaxed, these papillae stay flat, producing skin that looks and feels smooth, closely resembling the texture of open sand or drifting seaweed. When contracted, those same papillae rise sharply, creating a rough, spiky, three-dimensional texture across the skin, closely resembling coral, rock, or other jagged natural surfaces. This shift can happen in less than a second, controlled directly through the same nervous system responsible for colour changes across the body. Smooth to spiky, and back again, essentially in the blink of an eye. Picture bubble wrap that could switch between perfectly flat and fully popped. On command, instantly, then reverse itself just as quickly, over and over, without ever actually damaging the material underneath. That comparison captures something of the mechanical strangeness involved here. Texture appearing and disappearing, almost like a switch being flipped, except accomplished entirely through living muscle, instead of any kind of external mechanism. This texture control adds a critical dimension that colour changes alone could never achieve on their own. A predator does not rely purely on eyesight when investigating something suspicious nearby. Touch, and the general sense of a surface's overall shape, factor into that same assessment as well. An octopus that changes only its colour while leaving its actual physical texture completely smooth and obviously soft risks the entire disguise falling apart the instant anything makes even brief physical contact. By coordinating texture alongside colour, this animal builds a disguise that holds up under more than just a passing visual glance. A predator that brushes against jagged, rough-feeling skin, expecting to encounter coral or rock, receives sensory confirmation that closely matches what its eyes are already reporting, reinforcing the illusion rather than immediately breaking it apart. Researchers studying cephalopod camouflage broadly have noted that this particular texture-changing process remains considerably less understood than the mechanics driving colour change, largely because papillae movement proves genuinely difficult to observe and measure with real precision, especially out in open water under natural field conditions rather than inside a controlled laboratory setting. That gap in scientific understanding is worth acknowledging honestly. Colour changes have been extensively studied, mapped, and reasonably well explained through documented research. Texture changes, while clearly observed and confirmed as real, still hold on to real mystery regarding the exact fine details of how papillae coordinate so precisely and so quickly across the entire body at once. What remains completely certain is the overall result. A disguise built from colour and texture working together in tight coordination creates something considerably more convincing and considerably more dangerous to any predator willing to test it directly than colour alone could ever manage on its own. Texture changes involve more than simply raising or lowering flat bumps across the skin's surface. The actual structures responsible, called papillae, represent a genuinely sophisticated piece of biological engineering, one that scientists are still working hard to fully understand even today. Each individual papilla functions essentially as a tiny, muscular hydrostat, a structure built entirely from muscle, with no internal bone or rigid supporting structure of any kind involved. That description might sound oddly familiar, and it should. And it is the exact same basic engineering principle behind the octopus's entire boneless arm, just shrunk down dramatically, repeated many thousands of times across the surface of the skin itself. When a papilla contracts, it can push upward and outward, forming a distinct three-dimensional bump or spike rising directly off the skin's surface. Depending on how many individual papillae activate together, and precisely how each one shapes itself, the resulting texture can range from small, subtle bumps all the way up to larger, more dramatic spikes, closely resembling coral polyps, rocky outcroppings, or clumps of surrounding seaweed. Picture a bedsheet with hundreds of small motors sewn invisibly underneath its surface, each individual motor capable of pushing a tiny section of fabric upward into a distinct bump on command, then instantly retracting it flat again. Coordinate enough of those tiny motors working together, and the flat sheet could convincingly resemble a mountain range or a rocky, uneven surface, all built from a material that was originally completely smooth and featureless. Something remarkably similar happens across octopus skin, except built entirely from living muscle tissue rather than any kind of mechanical device. Scientific research indicates that papillae are controlled through motor neurons projecting directly from the brain, the same fundamental control system responsible for coordinating chromatophores and driving colour changes across the body. This shared control system helps explain how colour and texture manage to shift together in such close, tight coordination, rather than each system operating independently on its own separate timeline. Some cephalopod species studied more closely in laboratory settings, though not always this exact species specifically, have demonstrated the ability to recreate remarkably specific and detailed three-dimensional textures, closely matching individual rocks, tufts of algae, or even, in truly extreme cases, the general shape and silhouette of nearby coral formations. Researchers studying cuttlefish, a close cephalopod relative that has been more extensively studied under controlled laboratory conditions, discovered something particularly telling. These animals appear to rely primarily on eyesight rather than touch when initially deciding exactly which texture pattern to display. In other words, the octopus, or its close relatives, look first, assess the surrounding surface visually, then translate that visual information directly into a matching physical texture across their own skin. That finding raises a genuinely fascinating question about the deeper processing happening somewhere inside this animal's distributed, unusual nervous system. Somehow, visual information about an external surface gets translated into a specific, coordinated muscular texture response across the body's entire surface. Understanding precisely how that visual to muscular translation actually works remains one of the significant open questions researchers are still actively working to answer. Everything described so far assumes a fairly straightforward chain of command. Eyes detect the surrounding environment, the brain processes that visual information, then the brain sends signals outward to chromatophores and papillae, triggering the appropriate colour and texture response. Research conducted on closely related octopus species suggests that simple chain of command may not tell the complete story. Scientists studying a close relative, the California two-spot octopus, made a genuinely surprising discovery. Skin removed from these octopuses, physically separated from the brain and central nervous system entirely, still responded directly to changes in surrounding light levels. Something in the skin itself was sensing light, completely independent of the eyes or brain. researchers identified the specific protein responsible, a light-sensitive molecule called rhodopsin, the very same molecule found inside the eyes of humans and most other animals capable of vision. Finding that molecule embedded directly within skin tissue, far outside any actual eye structure, genuinely surprised the scientific team conducting the research. Picture a bedroom where every individual wall somehow contained its own small window, quietly sensing available light on its own, completely independent of whether the main window in the room happened to be open, closed, or even present at all. That comparison captures something of the strangeness at work here. Skin that senses light directly, without necessarily waiting for the brain to notice something first and issue a specific command in response. This discovery supports a broader concept researchers call distributed sensing, the general idea that perception and response in cephalopods generally may not remain strictly centralized within the brain the way it typically does in humans and most other vertebrate animals. Instead, individual patches of skin appear capable of responding somewhat independently to local conditions, adjusting nearby chromatophores directly based on light hitting that exact specific area, without necessarily waiting for full brain coordination first. This does not mean the brain plays no role whatsoever in the overall process. Broader, larger-scale patterns, deciding to become a sea snake instead of a lionfish, for example, still clearly require centralized coordination across the entire body at once. But smaller, localized adjustments, fine-tuning brightness, or contrast in one particular small patch of skin, based on immediate nearby lighting conditions, may happen locally, at the skin level itself, without requiring a full round trip through the brain first. Consider how a large company might actually operate most efficiently in practice. Central leadership sets the overall direction and major strategic goals, while individual local teams handle smaller daily decisions independently, without needing to check in through a lengthy formal approval chain for every single minor detail along the way. Something functionally similar may be happening within octopus skin. Small local decisions handled locally and quickly, while bigger, whole-body decisions still require full central coordination from the brain itself. Research specifically confirming this exact mechanism in the mimic octopus itself remains ongoing, since most direct experimental work so far has focused on other, more commonly studied octopus species instead. Still, given how closely related these species are, and how broadly shared cephalopod skin biology tends to be across different species, similar light-sensing abilities operating within this specific animal's skin seem genuinely plausible, and an active area scientists continue investigating closely. If confirmed fully, this would mean the octopus's skin is not merely a passive screen, simply displaying commands issued entirely from the brain above. It would mean the skin itself is quietly participating directly in the process, sensing and to some real degree responding, largely on its own. Here sits one of the strangest, most genuinely unresolved puzzles in this entire story. Substantial scientific evidence suggests octopuses may be colorblind in the traditional visual sense, lacking the specific type of color detecting cells found in human eyes and many other vertebrate animals, and yet this same animal reliably produces some of the most visually convincing color-based disguises found anywhere across the entire animal kingdom. That combination should not logically work. How can an animal lacking the eye-based hardware needed to distinguish red from green consistently produce convincing, color-specific impressions of a red-banded lionfish or a black and white striped sea snake? Researchers have proposed a compelling partial explanation. Rather than matching color precisely, the octopus may instead be matching brightness patterns, essentially the relative light and dark contrast found across a given scene, rather than truly matching specific colors themselves in any conscious visual sense. Many of this animal's key ocean predators, sharks, prominent among them, are themselves colorblind as well, relying primarily on contrast and overall pattern recognition, rather than true color vision to identify potential threats or prey nearby. Under that framework, the octopus does not necessarily need genuine color vision at all to fool a colorblind shark successfully. It only needs to accurately match the pattern of light versus dark, the overall contrast and shape, regardless of whether it can consciously perceive the specific colors involved in creating that pattern in the first place. Picture someone completely colorblind still managing to sketch a remarkably convincing black and white pencil portrait, capturing shading, contrast, and overall shape with real skill and accuracy, despite having no direct personal access to the full colour information a fully sighted artist might normally rely upon. The final sketch can still look convincing to any viewer, colourblind or not, purely through skillful use of light, shadow, and contrast alone. Some scientists studying this puzzle have proposed an intriguing additional theory, worth mentioning specifically as informed speculation rather than settled, confirmed fact. The light-sensing proteins found directly within chromatophores themselves, the same specialised skin cells responsible for producing colour, might potentially allow the skin to detect certain aspects of colour locally, at the specific cellular level, even if the octopus's actual eyes cannot process full, complete colour vision in the more traditional sense most people are familiar with. If that particular theory holds up under further, more rigorous testing, it would mean this animal effectively sees colour through its own skin, rather than exclusively through its eyes, a genuinely strange, almost science fiction sounding possibility that active ongoing research continues investigating closely. What remains completely undisputed, regardless of which specific explanation eventually proves correct, is the consistent, observable result. Convincing colour-based disguises produced reliably by an animal that may lack traditional colour vision entirely. Scientists themselves openly acknowledge this specific gap in current understanding as one of the more genuinely unresolved mysteries still surrounding cephalopod camouflage broadly, this species very much included. Sometimes the most honest, accurate answer in science is a direct acknowledgement. Nobody fully knows yet, not with complete certainty. And that open, honest uncertainty makes the underlying mystery even more genuinely compelling to sit with. Every disguise, every rapid decision, every precisely coordinated colour and texture shift described throughout this journey depends on some kind of nervous system controlling and coordinating it all. What that nervous system actually looks like, though, breaks almost every assumption most people carry about how a brain is supposed to work. This octopus possesses 9 separate brains. One central brain, located in its head, roughly donut-shaped, wrapped directly around its esophagus, and 8 additional smaller brains, called ganglia, one embedded within each individual arm. Compare that to the human nervous system, built around one single, centralised brain that directs essentially every conscious decision the entire body carries out. Even reflexes, technically bypassing full conscious brain processing for speed, still ultimately route back through the central nervous system for broader coordination and oversight. This octopus operates on an entirely different underlying model. Each individual arm brain can process sensory information and initiate certain movements largely on its own, without necessarily waiting for a command to travel first through the central brain and back out again. Picture 8 different students working together on a shared group project, each one capable of independently reading assigned material, solving their own individual piece of a problem and making reasonable decisions on their own, while still receiving occasional broader direction and coordination from one designated team leader, overseeing the whole group. That loosely captures something of how this distributed system appears to function, though the underlying biological reality proves considerably stranger and more tightly integrated than any human group project comparison could ever fully capture. Scientists estimate that a substantial majority of this animal's total neurons, by some informed estimates as much as 60%, reside directly within its arms, rather than inside its central head brain. That statistic alone should genuinely reshape how anyone pictures where the real thinking happens inside this creature's body. A human losing an arm loses a limb, but their brain, their memories, their capacity for thought all remain completely intact and unaffected elsewhere. An octopus losing an arm loses a meaningful portion of its total processing capacity as well, since a real, functioning piece of its distributed nervous system lived directly inside that specific, now missing limb. This distributed structure likely helps explain the speed and complexity behind everything covered across this entire journey. Coordinating disguise selection, precise arm posture, dynamic skin colour, and physical texture simultaneously, all within mere seconds under direct, immediate threat, would represent an enormous processing burden for one single centralised brain to manage entirely on its own, especially fast enough for genuine survival value in the moment, by distributing significant portions of that overall processing load directly out into the arms themselves. Each specific arm potentially handles much of its own local sensory input and physical response, freeing the central brain to focus primarily on broader, whole-body strategic decisions instead, like which specific disguise best matches the current approaching threat. 9 brains working together as one single, coordinated, functioning animal. That structure alone marks this creature as one of the strangest and most genuinely unique nervous systems found anywhere across the entire animal kingdom, and it directly sets up an even stranger, more specific question still waiting to be explored. What exactly are those 8 separate arm brains actually capable of accomplishing entirely on their own? Each of the 8 arms belonging to this octopus functions as something considerably more sophisticated than a simple, passive limb waiting patiently for instructions to arrive from the central brain above. Scientific research indicates these arms can independently taste and touch their immediate surroundings, and can control certain basic movements directly, without requiring constant, ongoing input travelling back and forth from the central brain the entire time. An arm exploring a dark crevice, searching for hidden prey, can process what it encounters and adjust its own movement accordingly, largely on its own, in real time. This capability connects directly and meaningfully to the disguise behaviours covered extensively throughout this entire journey. When 6 arms tuck tightly out of sight, while 2 arms simultaneously stretch outward to form a convincing sea snake shape, that entire complex manoeuvre does not necessarily require the central brain individually tracking and directing all 8 arms with equal, constant attention throughout the process. Local arm-based processing may reasonably handle a meaningful portion of that overall physical coordination directly, on its own. Picture a skilled pianist's hands moving rapidly and precisely across the keys during a well-rehearsed, practiced piece. The conscious mind sets the overall intention, playing this particular song at roughly this specific tempo, but the actual precise finger-by-finger movement often runs on something closer to trained muscle memory, requiring dramatically less moment-to-moment conscious oversight than the sheer physical complexity involved might initially suggest. Octopus arms may operate on a broadly similar underlying principle, though considerably more advanced and more independently capable than human muscle memory ultimately allows for. One particular detail illustrates this independence especially vividly. According to researchers who study octopus neurology and physiology, an arm that becomes separated from the rest of the body can continue reaching toward and even attempting to grasp nearby food for a period of time afterward. That single behaviour alone reveals just how much genuine local processing capability lives directly within the arm itself, largely separate and distinct from the central brain located elsewhere in the head. This distributed structure fundamentally challenges a very common, deeply ingrained human assumption. The assumption that intelligence and coordinated decision-making must always flow outward from one single, central command point. This octopus instead demonstrates something closer to a genuinely cooperative network, where meaningful decisions get made at multiple different points throughout the body simultaneously, rather than exclusively from one single central authority located in the head. Scientists studying octopus cognition broadly have described this general body structure as, in some genuine sense, blurring the traditional boundary of where the brain itself actually begins and where it clearly ends. Unlike a human, whose entire nervous system remains clearly centered around one identifiable central brain, this octopus is, in a very real biological sense, thinking with its entire body all at once, not with one single isolated organ operating in isolation from everything else. That blurred boundary helps explain, at least in part, how such an astonishing range of behaviours, 16 or more distinct disguises, each one requiring precise coordinated arm positioning, alongside simultaneous colour and texture changes, all get executed successfully within mere seconds, under direct, immediate threat with essentially zero room for costly error. Zoom in even further, past the level of an entire arm, down to a single individual sucker, and the sheer complexity involved only continues to deepen and expand. Each individual sucker lining an octopus arm may contain as many as 10,000 neurons, according to current scientific estimates, dedicated specifically to processing taste and touch information gathered directly at that exact precise location. A single arm typically carries somewhere between 1 and 200 individual suckers running along its length. Multiply that consistently across all 8 arms combined, and the total sensory processing capacity involved becomes almost genuinely difficult to fully comprehend or picture clearly. Humans experience taste almost entirely through the tongue, concentrated within one single, specific location inside the mouth. This octopus experiences a functionally similar sense of taste through literally hundreds of individual points scattered across its entire body, each sucker capable of directly sampling and analysing the surrounding water and any nearby surface it happens to make physical contact with. Picture a hand covered entirely in working taste buds, capable of identifying the specific chemical composition of anything it happens to touch, instantly, without needing to first lift that object up toward the mouth for a conventional taste. That comparison captures something genuinely real about how this animal actually experiences and processes its immediate surrounding environment. This capability directly supports the broader hunting strategies described earlier throughout this journey. When the octopus explores a dark crevice or an unfamiliar burrow while actively hunting for hidden prey, its arm does not necessarily need to rely purely on eyesight to correctly identify potential food. The sucker itself can directly taste and assess whatever it happens to touch along the way, gathering rich chemical information the eyes alone could never fully provide on their own. This same rich sensory capability likely factors meaningfully into the crab decoy trick described earlier as well. Successfully approaching close enough to convincingly imitate a potential mate requires extremely fine, precise control and constant sensory feedback, adjustments this animal can make in real time based partly on direct, continuous physical information gathered straight from its own actively exploring arms and suckers. Scientists studying cephalopod neurology broadly have noted that this distributed, decentralized sensory architecture likely evolved specifically because these animals, lacking any rigid protective shell of their own, need to explore tight, narrow, potentially dangerous spaces directly with their vulnerable arms, gathering rich, detailed sensory information immediately, well before fully committing that arm and the rest of the connected body any further into a potentially risky space. 10,000 neurons dedicated to processing taste and touch, packed inside one single sucker, repeated many hundreds of times across the entire body. That density of localized sensory processing helps explain, at least in significant part, how this animal navigates and hunts so effectively within its complex, murky, and often genuinely dangerous underwater environment, relying on far more than eyesight alone to make sense of the world immediately surrounding it. Among every strange and startling fact covered throughout this entire journey, this next one may be the single most difficult for many people to fully accept and process. Scientific observation confirms that an octopus arm, once physically separated from the rest of the body, can continue moving purposefully for a meaningful period of time afterward, including reaching directly toward nearby food. This is not simple, involuntary muscle twitching, the kind familiar reflexive response seen occasionally in many disconnected animal tissues generally. Documented observation shows something considerably more organized and purposeful than that. A detached arm can display coordinated directional movement, actively reaching toward a specific nearby food source, behavior that looks recognizably intentional rather than random or purely reflexive in nature. How is any of this even remotely possible? The clear answer connects directly back to everything already covered regarding this animal's uniquely distributed nervous system. Because each individual arm contains its own dedicated, semi-independent brain, a ganglion capable of processing sensory information and directly controlling movement on its own, a good portion of that specific arm's overall functional capability does not actually depend on a continuous, ongoing connection back to the central brain located in the head. Picture a branch office capable of continuing certain day-to-day operations for some meaningful period of time, even after losing direct real-time contact with the company's central headquarters. Not every single decision requires headquarters approval. Some genuinely useful, reasonably local decisions can still get made and carried out entirely on site, at least for a limited window of time, using locally available information and existing local authority. For this octopus, in the wild, this particular ability likely carries genuine and significant survival value. If a predator manages to catch and hold on to one arm during an active attack, the octopus can potentially detach that specific arm entirely, similar in basic concept to how a lizard might voluntarily drop its tail when captured, then escape while that separated, sacrificed arm continues moving independently for a period of time afterward, potentially distracting the predator further while the rest of the octopus's body actively swims away towards safety. This ability directly reinforces a genuinely important point about how fundamentally different this animal's entire nervous system truly is compared to a human's. For a human being, losing a hand does not mean that specific detached hand can continue moving and functioning independently on its own for even a brief moment afterward. The brain remains the singular, sole source of essentially all voluntary movement and coordinated action throughout the entire human body. For this octopus, a meaningful portion of what functions as thought, or at least as clearly coordinated, purposeful action, appears to exist directly within the arm itself, not solely and exclusively within the central head brain located elsewhere in the body. This single, striking fact helps tie together much of what earlier chapters have already explored regarding this animal's unusual biology. The extraordinary speed of its disguise transformations, the remarkable fine coordination visible across its skin, the sheer overall complexity of behaviour demonstrated by an animal possessing no centralised skeleton and no single, dominant brain in anything resembling the traditional, familiar vertebrate sense most people are used to thinking about. Beyond raw physical disguise ability, meaningful scientific evidence suggests these animals may possess genuine learning capabilities as well, including one specific skill long assumed to belong almost exclusively to vertebrate animals alone: observational learning. In carefully controlled laboratory experiments, researchers presented octopuses with a genuinely challenging physical puzzle: a securely sealed jar containing a piece of food hidden safely inside, requiring the octopus to work out exactly how to open it successfully. Octopuses that had previously watched another octopus successfully solve that exact same puzzle went on to solve it considerably faster themselves, compared to octopuses that were never given the opportunity to observe a successful demonstration beforehand. That specific result matters considerably more than it might initially appear to on the surface. Learning purely through individual direct personal trial and error represents one identifiable, well-documented type of intelligence. Learning instead by carefully watching someone else's prior successful attempt, then correctly applying that same observed lesson to your own separate situation, requires something functionally different and arguably more sophisticated: a working, useful understanding that another individual's actions can meaningfully inform and improve your own future behaviour and choices. Picture a new student joining an unfamiliar school partway through the year, quietly watching another student successfully navigate a confusing, complicated hallway shortcut, then confidently and correctly using that exact same shortcut themselves the very next day, without ever needing to personally get lost first while individually trying to work it out. That represents genuine observational learning in action, applying someone else's already demonstrated successful solution directly to your own separate individual situation. Scientists studying this specific finding have suggested it may point towards some limited form of theory of mind, a general cognitive capacity to recognize that another separate individual's actions can carry meaningful information directly relevant and useful to yourself. This particular capacity was long assumed to require a complex centralized vertebrate-style brain, not a nervous system as strange, unusual, and fundamentally distributed as the one covered throughout the last several chapters. This capability connects meaningfully back to the elaborate disguise behaviors explored extensively earlier throughout this journey as well. While the specific disguises used by this particular octopus species appear substantially instinctive in overall origin, the animal's broader general capacity for learning, problem-solving, and behavioral flexibility suggests a nervous system genuinely capable of considerably more than simple, pre-programmed, fixed reflexive action alone. An animal that can watch, learn, and meaningfully improve based on someone else's prior experience is demonstrating something recognizably close to genuine intelligence, regardless of how dramatically different its underlying brain structure happens to look compared to a human's or a dog's or any other more traditionally studied, more conventionally structured vertebrate nervous system. This growing, still developing picture of real octopus intelligence adds meaningful additional weight to every single disguise, every rapid decision, and every precisely coordinated physical transformation covered throughout this entire journey so far. This is not simply a soft-bodied animal blindly running fixed, pre-programmed instinctive scripts. It is an animal apparently capable of assessing genuinely novel situations, learning meaningfully from indirect observation, and adapting its own behavior accordingly, in ways scientists are still actively working to fully understand and describe with real precision. In July of 2011, a researcher diving off the coast of Indonesia noticed something that initially made no logical sense at all. Swimming directly alongside a mimic octopus was a small fish, closely matching the octopus's own brown and white banded colouring, moving in a way that made the small fish genuinely difficult to distinguish from the octopus's own trailing arms. That fish turned out to be a species of jawfish, a small, typically shy and reclusive fish that normally spends nearly all of its adult life staying extremely close to a small protective burrow dug into the sand, retreating instantly, tail first, at even the slightest hint of any nearby predator. Seeing one voluntarily swimming out in open water, far from any burrow, already struck the researcher as unusual and worth investigating closely. What made the moment genuinely remarkable was the fish's specific colouring and behaviour. It had adjusted its own natural colouring to closely resemble the octopus's distinctive brown and white banding, and it stayed tucked in tight alongside the octopus's arms as the octopus moved steadily across the open sand, effectively using the octopus itself as protective moving cover. Researchers who studied and documented this specific interaction described it as a case of opportunistic mimicry. The jawfish was not born with permanently fixed colouring specifically evolved to match this one particular octopus species. Rather, this specific jawfish population appeared to be taking clever advantage of a rare, unusual, situationally available opportunity, sharing directly in the octopus's own well-established, hard-earned reputation for safety and danger avoidance. Picture a nervous, quiet freshman closely shadowing a well-known confident senior through a crowded, potentially intimidating school hallway, matching that senior's general walking pace and posture closely, correctly betting that nobody bothered enough to specifically challenge the senior is likely to bother separately challenging whoever happens to be walking closely alongside them either. This finding adds a genuinely fascinating additional layer directly on top of everything already explored throughout this entire journey. The mimic octopus itself survives largely by convincingly impersonating more dangerous animals, and now, at least in this one specific carefully documented case, a completely separate species has apparently found a way to further benefit directly from the octopus's own already well-established disguise, without needing to develop and evolve any comparable disguise ability of its own from scratch. Researchers specifically noted that this exact pairing appeared to represent a genuinely rare occurrence, since the broader jawfish species involved actually ranges across a considerably wider stretch of the Pacific Ocean than the mimic octopus itself, whose confirmed range remains considerably more limited and geographically restricted by comparison. Across most of that broader shared range, no octopus happens to be locally available for the jawfish to closely shadow and mimic in the first place. This particular partnership, therefore, likely depends entirely on both species happening to occupy the exact same specific patch of ocean at precisely the same specific time. An animal already famous throughout the ocean specifically for borrowing other creatures' reputations has, in this single remarkable case, apparently become something other separate creatures have started borrowing directly from in return. The disguise the mimic octopus itself built for its own individual survival has evidently proven convincing and effective enough that an entirely separate species now actively benefits from sheltering safely within that same well-earned reputation. Everything explored throughout this journey so far centers around one single, confirmed species, but researchers studying this particular animal suspect something considerably bigger may still remain hidden and undiscovered, waiting quietly in similar overlooked habitats scattered across the wider tropical world. The mimic octopus itself was originally discovered and remains most reliably found, specifically within muddy river mouths and silty coastal bottoms, not within the bright, colourful coral reefs that draw the overwhelming majority of divers and dedicated marine researchers alike. That specific habitat, plain-looking, murky, and generally unglamorous by most conventional standards, went almost completely unexplored by serious dedicated researchers for a very long time. Scientists studying this species have specifically suggested that additional mimic species, potentially closely related to this one, or possibly representing something else entirely new and unknown, may very well exist within similar muddy river and estuary habitats scattered elsewhere across the broader tropics, areas that generally remain comparably unexplored and understudied for many of the same basic underlying reasons. Picture an enormous library where the vast majority of visitors, and even most professional librarians, only ever browse the front display shelves near the main entrance, while the vast, sprawling back rooms filled with genuinely older, dustier, less immediately organised material remain almost completely unexplored and effectively unknown, year after year. Muddy tropical river mouths represent something functionally similar within the broader context of ocean research, a genuinely vast, mostly unexplored backroom, hiding directly beneath waters most researchers routinely swim straight past without a second thought. This specific possibility carries real, significant weight precisely because of how late this particular species was originally discovered by science in the first place. Not identified in some genuinely remote corner of the deep, largely inaccessible ocean, but instead found in relatively shallow, easily reachable coastal water, close enough to shore for local fishermen to have quietly and informally noticed for generations beforehand. If an animal this visually striking, this genuinely elaborate in its overall behaviour, managed to remain fully undocumented by science until 1998, it raises an obvious and pressing question. What comparably remarkable animals might still remain waiting, quietly hidden in broadly similar overlooked habitat? Marine biologists have specifically pointed toward mangrove estuaries, silty river deltas, and murky coastal bays scattered throughout the wider Indo-Pacific region as genuinely promising locations still worth focused, dedicated future exploration. These specific habitats share the exact same basic core features that likely helped conceal the mimic octopus itself for so many centuries beforehand: poor overall visibility, unglamorous general appearance, and comparatively minimal historical research attention and dedicated scientific interest. This broader possibility connects meaningfully back to something explored earlier throughout this journey: the sheer scale of how much of Earth's ocean still genuinely remains unmapped, uncatalogued, and largely unexplored by dedicated science, even today. An animal this remarkable managed to hide successfully in plain sight for as long as recorded scientific history existed. Other animals, potentially just as remarkable and just as visually striking, may well be doing precisely the same thing right now, at this very moment, in a patch of quiet, overlooked mud that nobody with a camera has yet taken the time to properly examine. For years, the accepted, well-documented range of this species remained fairly narrow and well-defined, centered primarily around Indonesia, with additional scattered confirmed sightings across Malaysia, the Philippines, and parts of the broader Red Sea region. Then, a specific set of sightings recently expanded that entire picture dramatically, and rather unexpectedly. Marine researchers working specifically in Mozambique, located along the eastern coast of southern Africa, successfully photographed and confirmed a mimic octopus present within local coastal waters there, marking a genuinely significant, previously unrecorded expansion of this species' broader known range, roughly 3,000 miles from the Red Sea, and even farther still from the Arabian Sea, two of the previously closest confirmed sighting locations on record. Researchers involved directly in the discovery described their own reaction candidly as one of considerable surprise. Spotting a mimic octopus specifically within Mozambique felt instantly unexpected, precisely because virtually nothing in this species' previously documented established range had ever suggested it might successfully extend anywhere near that particular region of Africa. Picture discovering a specific, well-known species of backyard bird, one every serious birdwatcher confidently assumed lived only somewhere within North America, suddenly and unexpectedly turning up instead in South America, thousands of miles beyond where anyone reasonably expected to encounter it. That is roughly the scale and genuine surprise involved in this particular discovery. This finding raises two entirely separate, equally interesting underlying possibilities, and researchers have not yet fully determined with complete confidence which explanation, or possibly which specific combination of both, ultimately accounts best for what they actually observed and documented. The species might have always quietly existed within this broader region, previously undetected simply because comparatively few dedicated researchers had ever closely searched that particular muddy, silty stretch of coastline before. Alternatively, the species' broader overall range might genuinely be expanding outward over recent time, potentially connected to shifting ocean conditions or other broader underlying environmental factors still being actively studied and investigated. Either explanation reinforces a broader recurring point already made repeatedly and consistently throughout this entire journey. This specific animal excels more than almost any other documented species at remaining consistently undetected. An expanded range does not necessarily mean the species is only just now moving into genuinely new territory for the first time. It may simply mean researchers only just now finally managed to catch the species successfully doing what it has quietly and effectively done all along, undetected, in a location nobody had previously thought closely enough to carefully check. This discovery also carries real, practical significance for future research directions moving forward. If this specific species can successfully turn up literally thousands of miles beyond its previously well-established and confirmed range, then the true, complete extent of where it may actually live remains considerably less well understood than researchers had previously and confidently assumed. A species already famous throughout the scientific community, specifically for defying easy, confident expectations, just added one further genuine surprise directly to that already growing, expanding list. Discovered shockingly late, behaviourally unlike almost anything else recorded anywhere else in the animal kingdom, and now its confirmed geographic range has abruptly expanded by thousands of miles, entirely on the strength of one single, unexpected, carefully documented photograph. Step back now, away from any single specific disguise or any one particular scientific detail, and consider the complete overall picture this animal represents, taken together as one unified, coherent whole. Here is an animal carrying no shell, no bones, no venom worth genuinely mentioning, and no claws or teeth built for any kind of serious physical combat. By almost any traditional conventional measure of physical strength or defensive capability, it should rank among the more consistently vulnerable creatures found anywhere across the reef, and yet it survives, successfully, in one of the most densely predator-filled environments found anywhere on the entire planet. It manages this successfully, not through raw physical power, but through genuinely careful, precise observation, rapid situational assessment, and remarkably flexible, adaptable behaviour. It reads each specific threat as it appears. It selects, from an entire library of at least 16 distinct known disguises, exactly the one option most likely to work successfully against that particular threat in that particular moment. It executes that chosen disguise with a level of speed and precision that would genuinely impress even the most skilled professional human costume designer, working with far more time, resources, and advanced preparation available. Picture two entirely different students facing the exact same difficult, high-stakes challenge. One relies purely on raw physical size and strength alone to push directly through any given obstacle in their path. The other instead relies on careful observation, situational awareness, and thoughtful adaptability, reading each new individual situation correctly, then responding in whichever way best specifically fits that unique moment. Both general approaches can succeed under the right specific circumstances, but the second approach tends to prove considerably more flexible and broadly reliable across a genuinely wide range of different, unpredictable situations over time. This particular octopus embodies that second approach, about as completely and thoroughly as any animal studied so far. Its entire survival strategy depends almost entirely on flexibility rather than raw physical strength, on rapid situational assessment rather than any fixed, single, unchanging defense mechanism. There is a genuinely broader lesson embedded directly within this specific animal's story. one that reaches well beyond marine biology alone. Vulnerability, in the traditional physical sense, does not automatically or necessarily translate into weakness overall. A soft, boneless, shell-less body, one entirely lacking any conventional weapon whatsoever, can still succeed and thrive, provided the animal possessing that body proves genuinely smart, watchful, and adaptable enough in how it consistently responds to danger. This general principle echoes well beyond the boundaries of the ocean itself. Physical strength represents only one single possible path toward genuine, lasting resilience. Careful observation, situational awareness, and real behavioral flexibility can prove just as effective, and sometimes considerably more broadly effective, across a much wider range of unpredictable challenges and circumstances over time. An animal with essentially no conventional weapons at all has, through nothing more than careful observation and remarkably adaptable behavior, become one of the single most successful and quietly celebrated survival stories found anywhere across the entire ocean. That is a genuinely remarkable overall achievement for any creature. It becomes considerably more remarkable still once every specific, individual piece of exactly how it accomplishes this feat gets carefully and fully understood. For every single detail this journey has carefully and thoroughly explored, genuine, significant gaps in current scientific understanding still remain. Being honest and direct about those specific gaps matters just as much as celebrating everything that has already been successfully confirmed and understood so far. Scientists still do not fully understand precisely how this animal reliably matches its selected disguise so specifically and consistently to each particular approaching threat. Is the process closer to genuine real-time conscious assessment, something reasonably comparable to actual decision-making in some meaningful sense? Or is it closer to a deeply and finely tuned instinctive response, evolved carefully over countless generations, but still not requiring anything resembling genuine conscious thought occurring in the moment itself? Researchers actively studying this specific question remain genuinely divided, and the current honest answer remains simply this: nobody fully knows yet, with complete scientific confidence. The exact true number of distinct disguises this species is fully capable of producing also remains genuinely unconfirmed. 16 stands as the current, carefully documented total, but researchers openly and consistently suspect the true number likely runs meaningfully higher, given how comparatively rare confirmed sightings of this specific species remain, even today, in the small handful of most reliable known hotspots. The precise underlying mechanism explaining how this animal manages to produce such convincing, detailed colour-based disguises, despite likely being colourblind in the more traditional visual sense, remains only partially and incompletely understood as well. The leading current theory, involving brightness and contrast matching rather than true colour matching, offers a genuinely reasonable partial explanation, but plenty of specific granular details still remain actively unresolved and under continued careful investigation. Exactly how finely and precisely the brain coordinates papillae, the specialized structures directly responsible for texture changes, remains considerably less well understood and researched compared to the chromatophore-based color-changing system. Researchers have openly and directly acknowledged this specific texture-based mechanism as measurably less studied overall, and therefore correspondingly less well understood compared to color changes. And the full, complete extent of this species' broader geographic range remains an open, genuinely active question as well, particularly following the recent, unexpected Mozambique discovery described earlier, which meaningfully expanded the previously accepted range by literally thousands of miles in one single, unexpected finding. Picture a genuinely detailed, carefully constructed map, largely complete and reasonably accurate across most of its overall area, but still containing several conspicuously blank spaces scattered here and there. Areas carefully and honestly labelled simply as unknown, rather than being confidently but incorrectly filled in with pure guesswork or unfounded speculation. That accurately describes the current, honest, overall state of scientific understanding surrounding this genuinely remarkable animal. These specific acknowledged gaps do not meaningfully diminish anything this journey has already carefully explored and documented. If anything, they meaningfully strengthen the underlying overall story being told here. This is a real, living, functioning animal, not a fully solved textbook puzzle, with every single piece already fitted neatly and completely into place. Researchers continue actively diving, actively filming, and actively studying this same species today, adding carefully to an already growing, evolving body of confirmed knowledge, one confirmed observation, one careful sighting, one peer-reviewed published study at a time. The full, complete story of this remarkable shape-shifting animal has not yet finished being written, and that specific, honest fact makes everything already covered throughout this journey considerably more exciting to seriously consider, not meaningfully less. Return, for a final moment, to that original muddy slope off the coast of Sulawesi back in 1998. A diver, hovering patiently just above the silt, filming what appeared at first glance to be nothing more than an unremarkable, forgettable flatfish gliding steadily across the sand. That single, quiet moment ended up rewriting a meaningful piece of what science confidently believed it already knew about animal behavior, camouflage, and mimicry throughout the natural world. Not because the ocean itself had somehow changed in any way. The ocean, and this specific octopus species along with it, had almost certainly been performing this exact same elaborate trick for millions of years beforehand. All of it happening quietly, completely unnoticed, and entirely undocumented by anyone. What changed, specifically, was simply this. Someone finally happened to look closely enough, patiently enough, and carefully enough, in precisely the right overlooked place, at precisely the right specific moment to finally notice. That single, simple fact carries real, genuine weight that extends well beyond this one specific, remarkable species. The ocean covers roughly 70% of Earth's entire surface. The clear, overwhelming majority of that vast surface remains, even today, considerably less explored and understood than the visible surface of the Moon. Scientists reasonably and openly estimate that a substantial majority of all ocean-dwelling species remain completely undiscovered and formally undescribed by science, even now in the present day. Picture walking confidently through a house you have personally lived inside your entire life, one you would naturally and reasonably assume you already know completely and thoroughly, only to unexpectedly discover an entire additional room tucked quietly behind a bookshelf, one that had apparently been there patiently the entire time, simply waiting for someone to finally look carefully enough to notice it. That is essentially what this single, unassuming octopus represents within the much larger context of the wider ocean itself. Not a genuinely rare, singular, one-time exception to how the natural world generally operates. Rather, a clear, striking, powerful reminder of just how much still quietly and patiently waits to be properly noticed, carefully studied, and eventually fully and completely understood. Consider everything this one single animal alone has already revealed. A creature capable of convincingly impersonating at least 16 entirely separate species. Skin containing millions of individually controllable colour cells. A nervous system distributed intelligently across 9 separate semi-independent brains. Texture-changing structures still not fully or completely understood, even by dedicated, specialised researchers. A confirmed geographic range that recently and unexpectedly expanded by literally thousands of miles in a single afternoon, based on nothing more than one careful, well-timed photograph. If a single, unassuming, boneless creature, hiding quietly in plain sight within shallow, easily reachable coastal water, could remain completely undiscovered by organised science until 1998, then the honest, sobering question becomes genuinely unavoidable. What else, right now, at this very moment, is quietly and patiently waiting in equally overlooked mud, equally overlooked water, simply for someone, somewhere, to finally take the time and patience needed to look closely enough to notice? The mimic octopus did not choose to hide from science specifically. It was simply, quietly, being exactly what it has always been, brilliant, adaptable, and endlessly capable of becoming something else entirely. Whenever survival genuinely demanded it, science just happened to arrive considerably late to a performance that had, in truth, been running steadily and continuously the entire time.